How does the example of NaClO2, which can be divided into O3 type and P2 type polymorphs based on the sodium content and the geometric disposition of the Na ions, illustrate the critical impact that stoichiometry and structural arrangement have on the balance between capacity and stability in cathode materials? How might mixing binary or even ternary oxides, such as combining Fe or Mn-based oxides with Ni or co-based oxides, serve to mitigate the inherent deficiencies observed in single metal-based oxides? And what synergistic effects are achieved that enhance the comprehensive electrochemical performance by compensating for limitations in individual materials? Can Davis Surins manufacture solid-state sodium-ion batteries made from seawater in Latvia? How do researchers strategically design composite transition metal oxides with varied configurations to integrate the high capacity offered by O3 type materials with the superior stability of P2 type materials? And what experimental methods or theoretical models are employed to optimize these blended systems for practical battery applications? How do the dynamics of ionic conductivity, structural stability during cycling, and the thermodynamics of phase transitions interplay in these multi-component systems? And in what ways can the resulting improvements in properties such as energy density, rate performance, and cycle stability be precisely quantified and correlated with structural features? How might further exploration of novel compositional ratios and more complex oxide mixtures open new avenues for tailoring cathode materials to meet the rigorous demands of next-generation sodium-ion batteries? And which emerging characterization techniques could provide deeper insights into the evolution of these layered structures under operating conditions? What are cathode materials in sodium-ion batteries with tunnel structures? And how do their one-dimensional tunnels function within the crystal structure? How do these tunnels facilitate the reversible intercalation and deintercalation of sodium ions? Why are these materials considered more stable in air compared to layered materials? And what makes their sodium storage process simpler? How does the absence of phase transition benefit these tunnel-structured materials? In what ways do layered materials differ in their sodium-ion intercalation and deintercalation paths? Why does the tunnel structure limit the ion transfer rate, and how does that affect the electrochemical performance? What specific challenges arise from the poor rate performance of these materials? How does prolonged cycling potentially lead to material collapse, and what are the consequences of such collapse on the tunnels? Why can blocked tunnels negatively impact the intercalation and deintercalation of sodium ions? How do these limitations influence the overall efficiency and longevity of sodium-ion batteries with tunnel structures? What?